Problem number 14, we have f and g, which are differentiable functions, and we know the following. We know that g is always positive, and we know that f of 0 is 1. We're given a third function, h, which is equal to f of x times g of x, and we're specifically told that h prime is f times g prime. Our goal is to figure out what f of x is equal to. And here are four options. F is either its own derivative, which seems weird, f is g, f is 0, or f is 1. Well, in order to figure this out, we have to go back to the original function h. We're told that h is the product of f times g, which means that if we were to take the derivative of h, we would have to use the product rule. And the product rule, we know, will lead us to the derivative of one times the other plus, and then the converse, the derivative of times g. So we see we're missing something here. So let's spell that out a little bit more. Let's do the product rule out for h of x. So h prime of x, the derivative of h, means we're going to derive the first and keep the second. So we're going to derive f, and we're going to keep g. And then the product rule says now add to that and switch it up. So plus, now we take the derivative of g, and we keep f of x. So this is what h prime of x should be when it's all drawn out. But we're specifically told that h prime of x is only the second part. It's only the g prime f. So what that means is that this first part right here must be 0 for this particular derivative. So that means one of two things. Either f prime of x is equal to 0, or it means that g of x is equal to 0. Because the only way that f prime times g is 0 is if one of these two is true. Let's go back to the given. We're told that g is always positive. So g can't be equal to 0. So that's out. That means that this is true. F prime of x is 0. Okay, so if f prime of x is 0, that means we can figure out what f is. We go back to our rules. If the derivative of a function is 0, what's the original function? Well, our first rule was the constant rule. We learned that if the function is equal to a constant, then the derivative of that function will be 0. So f of x is a constant. Well, there's only two constants that are choices, either 0 and 1. So they go out, a and b. So f is either 0 or 1. And there's still one piece of information we haven't used yet. The fact that when you plug in the value of 0, you get 1. Well, the only way, or the only one that can be true then is d, right? Because f of whatever, put any number that you want here, that will be equal to 1 if the function is 1. So f of 0 will be 1, that's true, d is our choice. And finally, number 15. Let's go up just a touch. All right, so we're back with another piecewise defined function. F is 2x minus x squared if x is less than or equal to 1. And f of x is x squared plus kx plus p if f is greater than 1. Part A says, what values of k and p will f be continuous and differentiable at x equals 1? Okay, so if we plug 1 into the original function, both the top and the bottom, because that's where our condition changes, they have to be equal to each other. So in other words, we're looking at the fact that 2x minus x squared must be equal to x squared plus kx plus p when x equals 1. That's what the continuity part tells us. In order for f to be continuous at x equals 1, these two have to be the same when x is 1. So let's plug 1 in for x. 2 times 1 is 2. 1 squared is 1. 1 squared is 1. K times 1 is k. And then we have our p. 2 minus 1 is 1. And if we subtract 1 from both the right side and the left side, we end up with the fact that k plus p is equal to 0. That is not enough information to tell us the values of k and p. We have to go one step further. We have to look at the differentiability part. Well, the differentiability part at x equals 1 means the exact same thing must happen, but at the derivative of f, not f itself. So we need f prime. We know that to derive a piecewise defined function, we just derive both, or all parts rather. So 2x minus x squared derives to 2 minus 2x, and we keep our condition. This is true when x is less than or equal to 1. And then we take the derivative of our bottom part, x squared derives to 2x, k times x derives to k, and p is a constant, so it derives to 0, and this is valid when x is greater than 1. So now we also know that 2 minus 2x must equal 2x plus k when x equals 1. Those two parts of the derivative must be equal to each other in order for the function to be differentiable at x equals 1. So once again, let's plug 1 into both of these. We have 2 minus 2 equals 2 plus k. So 0 is equal to 2 plus k, which means that k is negative 2. And if k is negative 2, and k plus p is 0, 0 is equal to negative 2 plus p, p must be 2. Find the value of f prime of negative 5. Well, negative 5 is less than or equal to 1. So we're going to plug negative 5 into the derivative of 2x minus x squared. Be careful, don't plug negative 5 in here. Plug negative 5 in there. So f prime of negative 5 is going to be 2 minus 2 times negative 5, which is a perfectly fine answer. If you choose to simplify it, we have 2 plus 10, or 12. But again, you don't need to simplify. Finally, write the equation of the line tangent to f at the point where x equals negative 1. So this is our x1. Remember, we're going to use our point slope form, like so. We're given our x1. We need our y1. y1 is the function's value at x1. So y1 is equal, there should be 1 down there. So y1 is equal to f of negative 1. If we plug negative 1 into our function, negative 1 is less than 1, so we have to plug negative 1 in here. So we end up having 2 times negative 1 minus negative 1 squared. That's negative 2 minus 1, which is negative 3. That's our y1 value. You always get the y1 value by plugging the x1 value into the original function. You always get the slope, which I'm going to do right up here, by plugging the x1 value into the derivative of the function. So our derivative is right here. We're interested when x is equal to negative 1, which is less than 1. We're going to plug negative 1 into the top part of the derivative. So our slope, which is f prime of negative 1, is equal to 2 minus 2 times negative 1. That means it's equal to 2 plus 2, or 4. So, going back to the original equation, we have y minus, our y1 value is negative 3, so that's actually y minus negative 3 or y plus 3, equals the slope, which we found to be 4, times x minus the x1 value, which is negative 1, so minus negative 1, which is the same thing as plus 1. And that answer is done. You don't need to turn that into slope-intercept form. You only had to write the equation. So we're done.